I've been sort of head down into the integration of boilers and pipework and thermal stores and control valves and control systems for probably about 5 years now, since I started work in earnest on the Biomass Guide CIBSE AM15 rather. As a result of that publication, largely over the last couple of years, we've been asked by clients from the north of Scotland to the very south coast of England to the west of Eire to go and have a look at boiler houses which either are not working properly or boiler houses which don't work at all. And as a result of that, I've accumulated quite a massive information about why systems don't work properly. And what I want to talk about this evening is that accumulated knowledge. So what I'm presenting to you is not what I think might happen. It's as a result of taking measurements and then modelling and analysis to demonstrate to the clients that these things do actually happen. And in many cases, we've been given the opportunity to go into some quite large boiler houses in some cases and completely re-engineer them to get them working properly. So we've looked at faulty systems, and most of the systems that we've been asked to look at have got biomass involved because I'm the one that wrote the Biomass Guide. But what we found was that when you start to dig in under the surface, that sometimes the biomass boiler is not to blame at all. It is the way it has been integrated hydronically into circuits and the way it is controlled or not controlled in relation to other boilers. So this is not per se about biomass. I speak about biomass endlessly. What I'm saying here applies equally to CHP. And the reasons why biomass doesn't work well enough or doesn't produce a great enough proportion of its energy, or the theoretical amount of energy that people think it should supply at the design stage, those arguments are equally applicable to CHP, because there have been numerous CHP units up and down the country where they have not run for the hours or produced heat for the hours that they were supposed to, and therefore the finances didn't stack up, and so on and so forth. So this is what I want to talk about this evening. The key things that we find, and I'm going to go through these in detail, are what I define as temperature dilution, which should be a well-known problem in the industry, and is something that as designers we all have to design out as far as possible. But I'm going to explain what gives rise to it, the maths behind it, how to detect it. Then the next thing I want to talk about is flow division. That if you've got 2 or 3 boilers or heat generators in parallel and they're all switched on, then the flow is going to divide between those boilers in the ratio of their flow rates. I'm going to talk about some of the really silly things that we've seen, what I call poorly understood retrofit design, and problems particularly with adding boilers running at a 20-degree delta T onto systems which were designed for 11, and that is quite a common one. And then the use of load modelling and vis-a-vis actual circuit performance, and how they often don't tie up. Now, throughout this seminar, I am not going to refer to any organisation, any particular building or institution, for obvious reasons. Some of the things that I find are quite sensitive. In some cases, we sign non-disclosure agreements. And if any of you have got a circuit that was underperforming, I'm sure that you wouldn't want me to go and spout that to the world at large. So please don't ask me where they are, who the clients are, what sort of buildings they are. But as you will see, the range that we have, range of properties we've looked at varies from large public sector buildings of all types to private sector buildings to social housing complexes and systems, and offices, you name it, it's in here. Okay, so this is very representative of the widest range of the types of buildings that we have in the UK. So if I start with flow and temperature dilution. Just over 2 years ago, I wrote an article in the CIBSE Journal in February 2014 on the design of header systems. And to set the scene, I wish to run very briefly through what I put there. This stuff, until I wrote AM15, the Biomass manual, these circuits and their descriptions have not been published anywhere previously in any subsea publication. So I put them out into the journal before they went into AM15. I asked for feedback from the community, the 20,000 odd people that read the journal. I got two people came back with minor comments, but nobody came back saying I was wrong, which is encouraging in a way, but it's also discouraging in that people, for the most part, don't seem to think about these things deeply, or if they do, there are those who just keep their head under the parapet. I remember speaking to the company that designed Terminal 5 at Heathrow, and they said that they'd spent a whole year modelling the header systems in Terminal 5 to make sure that they didn't have any of these problems. So our current practice is to have individually pumped boilers with a low loss or common header. And there is a difference between a common header. A common header is just a circulating pipe which circulates from the boilers back round to the boilers again. The purpose of it being to ensure that there's no induced flow in the load circuits when there's no load circuit demand. So in a low loss header, you run the water very slowly, 0.1, 0.2 meters a second in the header. That way there's no induced pressure between the flow header and the return header on the load side. That's the simple principle of it. The idea is that the flow should always be forward along the header from top to bottom. And then you get the load circuits pick off the header and return to the header. To do that, the flow rate on the primary side, which is the flow rate through the boilers, has always got to be greater than the flow rate through the load circuits. So if you've only got two boilers on, then the load circuit flow rates need to be reduced to match the flow rates through the boilers, for example, or if you've only got one boiler on. I'll come to what happens in a second. Now, this is a very frequently encountered arrangement. We see this more often than we see the previous arrangement with just a stub header and a... Now, if I just go back to that previous one briefly, this is often implemented as a hydraulic separator, which is just a vessel sort of that size, that diameter, with two pipes in and two pipes out. Right, that's the hydraulic separator header. We often get this arrangement. You can't mount that vertically, and the reason for mounting a low loss header vertically is if you've got a very low flow rate, any air is going to bubble to the top. More importantly, any sludge is going to drop to the bottom. If you have a horizontal header running at 0.1, 0.2 meters a second, it'll just gradually sludge up. And without some method of clearing that sludge, you've got a problem. So they should be mounted vertically, but when you design a header like this, you can't usually physically mount it vertically because you need a lot more space than height in the plant room. But the same rule applies, that the total flow on the primary needs to be greater than the total flow on the secondary. Now, when the total flow on the primary is less than the total flow on the secondary, you get partial reverse return up the header. So in this case, for example, the flow to circuit 1 at the top, right-hand side there, the load circuit 1, will be at the flow temperature coming off the boilers, but load circuits 2 and 3 to the loads will be receiving their water at return temperature, or at a mixture of return temperature and flow temperature, depending exactly where the mixing point between the flow and return is on the header. Now this, unfortunately, we find almost everywhere we go. I really would not have believed it unless I've seen it so many times, and we've seen 15, 16 instances of this now in the last few years on boiler houses from about 200 kilowatts up to 8 megawatts. If you wish to ensure a constant return temperature for condensing boilers, then you want to deliberately cause reverse return up the header. And Viessmann, this is one of their recommended configurations. They recommend a primary flow 30% greater than the secondary flow to make sure that it comes back on the return circuit at a constant temperature. Now, there's a publication which I'm about to comment on for CIBSE AM14, which is the non-domestic heating, and there are some significant issues with that publication, which the publications manager knows about, and we're going to write to them and suggest that the authors of that have a look at some of the things which are in there. And one of them was a recommendation to have a constant return temperature for condensing boilers, which by definition means the flow temperature is variable. And one of the diagrams in that publication has constant temperature circuits like hot water cylinders and fan coil units running on a variable temperature flow. Wasn't picked up before publication. So, okay, something that is done, and I remember that one of the very first headers I ever saw being made, they asked the contractor, why are you putting a non-return valve in the middle of the header? And the answer was to prevent reverse flow up the header. But doing that, you fall back into the old trap of just having no header at all, effectively, because when the flow rate on the primary is greater than the flow rate on the secondary, then the boiler pumps are in series with the load pumps, and you go back to the boilers in series, which we used to have when we designed split header systems with all the associated control issues. So if you see headers with non-return valves in the middle, it means there's probably a problem in the plant room, and you've effectively got a split header system. Now, individually pumped boilers are the current recommended method. The job which started this all off about 4 years ago for us, we were in a 3.5 megawatt plant room in a big organisation. Brand new plant room with a 300 kilowatt biomass boiler and the rest gas boilers. And all of the pumps were on the flows out of the boilers. And they were low water content condensing gas boilers. I think there were 500 or 600 kilowatt modules, lots of them. So we spoke to the manufacturer, and they had to scratch their heads. They said, "Yeah, no, they should really be on the flow, on the inlet to the boiler, not on the flow from the boiler." Now, most of the diagrams in AM14, the non-domestic heating manual, show the pumps on the flow. And that was the way we used to do it before the European Boiler Efficiency Directive kicked in and we started to have low water content boilers to get boiler efficiencies up. I have subsequently researched the British standards on which AM14 is based, and both the standards which recommend the pumps on the flows were both written about 5 to 8 years before the Boiler Efficiency Directive, and in the days when we used to use large water tanks in the roof to pressurize our systems. That's how out of date it is. All modern boilers should have pumps on the flow into the boiler for the reason that the high pressure loss component on a circulating header system is the boiler, it's not the header. You might have 30 or 40 kPa pressure drop in the boiler, but only 5 or 10 kPa pressure drop across the rest of the circuit. And the pump must make up for the highest pressure drop. If you put the pump sucking out of the boiler on the flow, then there's a very good chance, certainly on pump startup and also during operation, and especially if you're operating in the mid-80s to 90 degrees, that you will get kettling in the boiler, you'll get boiling of water in the boiler, because you'll have crossed the vapor pressure line within the heat exchanger in the boiler. Now, this particular job with this large boiler house and all the pumps in the wrong place, the manufacturers agreed with us. Then we had a meeting with the design team, a big London design team, and then also present were another big London design team who were there to check on the first design team. And they both got it wrong, and then they persuaded the manufacturer to say, no, it's okay to have the pumps on the flow from the boilers, just to save the backsides, which is a real shame. If you see installations with modern boilers with the pumps on the flow from the boilers, you could well have a problem. And the other problem is that the pumps will then pressurize the headers. So if I just go back a couple of slides, pass that one. All right, so if I go back to here, if the pumps are on the flow from the boilers, all of the pressure from the pumps which is required to overcome the loss in the boilers is actually pressurizing the header, and again you've effectively got pumps in series, because the pressure from the boiler pumps then pressurizes the inlet to the load pumps, and the whole point of putting in the low loss header is to isolate the load from the boiler side hydraulically, so that the boilers don't influence what happens on the load circuits. So if you've got low loss, the low water content, modern boilers, the pumps must be on the inlet to the boilers to make sure that the neutral point on the circuit is down here at the bottom of the header. And that's where you pressurize on the inlet to both sets of pumps. And of course sequencing has got to be on flow temperature. In this arrangement you can't sequence on return. Or it doesn't work so well. Right, now some diagrams from a very old, quite a few diagrams in here from a very old publication called GR41. I don't know whether you remember, it was produced about 25 years ago. And it set out recommended hydraulics schematics for all sorts of boiler arrangements and header arrangements. It really anticipated what was coming up with the European Boiler Efficiency Directive and the move from split headers to common headers, and set out the basic rules for it. So this is still as valid as the day it was written, but this comes with particular problems which I'm about to talk about. So temperature dilution. Right, if you have, and this is the only bit of maths tonight, chaps. If you have flow coming in from the top left at temperature T flow 1, TF1, can you read that at the back? Yeah. At flow rate m.1, mass flow rate 1, m.1. It's flowing out of a node at m.2 and flow rate and temperature flow 2. And a proportion of the return water goes up a bypass leg and mixes with the water from node 1. So you've got flow in from the boilers on node 1, you've got a return, partial return from the return circuit at node 2, and together they mix to cause a mixed flow temperature and reduced flow temperature at node 3. This is the basis of temperature dilution, which you start looking for it, you'll find it everywhere. Now to do the analysis on this circuit, it's a simple equation. It's the sum of the powers entering and leaving that node must be 0, because what comes out must go in and what goes in must come out. Okay? So if you take m dot Cp delta T for each of those nodes, 1 and 2 equals m dot Cp delta T3, or minus, that equals 0. And then expand again. Now, the delta T in this case, in these equations, is the temperature on the flow line at node 1, flow at node 2, or the return temperature, and it's got to be referenced to a temperature, because the delta T is not the difference between flow and return, it's the difference between flow and a reference temperature and the difference between return and a reference temperature. It works, believe you me. In that equation, the CP's will cancel out. And if you set the reference temperatures to 0 degrees, T-refs will disappear. And then that simplifies down to that. So basically you've got mass flow rate times temperature going in on node 1, plus mass flow rate times temperature going in on node 2, minus the mass flow rate times temperature going out on node 3 equals 0. And from that, you just rearrange that to give you the flow temperature going out of node 3 there as that equation. Now, we analyze a lot of circuits, and this is the only equation we use. And it's very simply implemented in Excel, as I'll show you an example at the end. Right, these are taken from GR41 publication on pumped systems. If you have 3 boilers and they are running at their full load, then this is in the days of 11 degree delta T design, then you would have an 11 degree temperature drop across the circuits. If you only have 60% load, so you have boilers 1 and 2 but boiler 3 off, but with flow still running through boiler 3, then you get return temperature from the common header, and because you've only got 60% of the load, you've only got 60% of 11 degrees C dropped across the header if the load circuit pumps are all constant flow rate. Yep. So the return flow that runs straight through boiler 3 mixes with the flow at 82 from the first 2 boilers and gives you a reduced flow temperature. And that's what I describe as temperature dilution. Now in GR41, against this diagram, the comment was, because you ran 8271, that if you drop the flow temperature from 82 down to 79.8, it's not really of any consequence. You don't really need to concern yourself about it. And that is, I think, for the most part, pretty true. If you're only losing a couple of degrees, except in the very, very coldest weather, you're not going to lose it. In the very coldest weather, all 3 boilers are going to be running anyway. So it's not of any great consequence in this example. If you now look at 30% load, well, you've got a much smaller temperature difference across the load circuits, so the return's coming back at a higher temperature. Again, you get 79.8 with only 1 boiler running at 30% load. So the basic principle of sequencing boilers to match the load works, but you do get a small drop, about a 20 or 25% drop in the flow temperature, or in the delta T, which if you're only running at 11 degrees is not particularly significant. But when you start running at 20 degrees, you're suddenly looking at 6 or 7 degree temperature drop from 80, and you're down to 74 or 73, and all of a sudden it starts to become important. So let me give you some current examples. Right. One other thing about the Scottish technical standards, which has still not been duplicated in the England and Wales technical standards, of course, we have to isolate our offline boilers. When you isolate a boiler offline, commonly you run a bypass around the boiler, sometimes with a pump in that bypass loop to cool the boiler down. And when you do that, then you're immediately effectively by putting the return water temperature straight back up onto the top circuit again. One of the reasons you need those bypasses, if you have a fixed speed pump in the return line, a common boiler pump as opposed to individual boiler pumps, if you have a common boiler pump, the only way to sequence the boilers on temperature is to have a constant flow rate, because if you've got m dot Cp delta T, if you're varying m dot, then you can't control on delta T, because you've got 2 variables and you're varying them both, which is one of the common control mistakes that you see from time to time. So if you've got a fixed speed pump and a single pump in that arrangement, you must have bypasses on the boiler to keep the flow rate constant, but then you get temperature dilution as a result of doing that. So if all 3 boilers are on there, the bypasses are not in circuit and you get the flow temperature out. But the minute that you take one of those boilers out of circuit, now we're on a 20 degree delta T, you can see the flow temperature drops to 76 at 6%, 60% load, and it goes to 77 at 45% load. And the reason the temperature comes up a bit is that at 45% load, you're only dropping 9 degrees of the 20 across the load circuits, if the load circuits are constant speed pumps. And then at 30% load, it goes down to 76 again. So what we've lost there is 4 degrees on the flow temperature, from 80 down to 76. And again, perhaps no great shakes if that was the end of the story, but unfortunately it isn't. And then that's the situation at 20% load. Okay, now what I find in practice, and because it involves biomass, and you say where you've got biomass boiler on the left, read CHP unit with or without that thermal storing circuit. What you find with biomass, and is that you have a biomass boiler driving a thermal store. The biomass boiler frequently is not designed to take the full load, and really should never be designed to take the full load, to make sure it works efficiently and that it's got sufficient turn down to meet summer loads. So you've got a biomass boiler which supplies less than the full load. That means that flow rate 1, Q1, in that loop to the thermal store will never be as large as Q3, which is the full load flow rate. So if you have the load pumps, which are constant speed pumps, by definition, you can have you can have flow rates 3 or possibly 2 and 3, which are greater than flow rate 1, and you will get temperature dilution. And the only way to avoid temperature dilution and to make sure that the temperature leaving the biomass boiler actually gets to the load circuits is to make sure that the flow rate on loop 1 is bigger than the flow rate on loop 2, and the flow rate on loop 2 is bigger than the flow rate on loop 3. That's how it should be designed. It's actually very difficult. This is what we find almost universally, that the biomass flow rate is less than the flow rate on the secondary side of the buffer vessel or thermal store, and then the total flow rate on the other side of the low loss header is even greater again. So here you have 2 stages of temperature dilution. You've got temperature dilution coming out of the thermal store, because that acts as a mixing node, and you've got temperature dilution at the top of the low loss header, another mixing node. So all of a sudden you can now be down at 70 degrees flow. One institution that we visited, that is what we measured. 4 stages of temperature dilution. We measured temperature dilution at every stage, and on the load side, because the building had biomass boilers retrofitted in an external plant room and pipes led in through a heat exchange and all the rest of it. And the facilities manager in this organisation was so frustrated he couldn't get the building hot. The building simply wasn't heating in the morning. So he then went along and he turned up the flow rates on all the load pumps, trying to get more heat out. And all he did was make matters worse. So that's as bad as it gets. We've seen this a few times, not quite as low as 54, but with several times we've seen temperatures onto load circuits down in the low 60s. And you've got a real problem even in winter. You've got a real problem with this situation. And because this is not published anywhere, and people generally don't take this wrong, but people generally don't understand it. It's only when you've gone to the lengths that we've been privileged to go in and find these problems and figure out what the problems are. And I'll be asking you at the end of this what we do with this information. This is very common. I reckon I can go to every other biomass boiler house that's been installed in the UK in recent years and find some degree of temperature dilution, and probably at least 2 stages of it. One stage taking you from 80 to 76 or 80 to 75, we can live with that. Taking you from 80 to below 70, you've suddenly got a real problem with your constant temperature circuits. We dealt with one really large building in the last few months where large parts of the building heated by wet radiant panel heaters in the ceiling in high halls with 10-meter roof spaces. And when you get below 70 degrees, they just do not heat up at all. And a retrofit to a boiler house had resulted in temperatures less than 70, and the client was tearing his hair out. And we got a panic phone call to go and visit him at very short notice to say, what on the earth's going on here? So avoidance. The first thing in design terms is to work back from the load circuits to the front end to see what's happening and what could be made to happen. And if possible, and I know load circuits are the Cinderella in much of what we do, especially when you're retrofitting. You focus on the boiler house, you do a really good job, and you get an excellent boiler house built. You think you've got it cracked, and if there's been no attention paid to what was happening on the load circuits before you added the new boiler house and how they need to match flow rates on the new boiler house, then all of a sudden you're in trouble, and people throw their hands up in horror and say, well, we don't understand what's happening. And it's this successive temperature dilution is what's happening. So converting load circuits to variable speed operation and then controlling them to maintain a constant delta T across the load circuit rather than controlling them on pressure. Because the tendency these days is, because large numbers of the variable speed pumps available have got pressure sensors built in, especially all the big ones do, then people just tend to use them and they set them into a proportional pressure mode and we've done the job. But it doesn't take any account of the fact that the flow rates might still be far too high on load circuits. If you've got any number of 3-port valves on fan coil units, air handlers, hot water cylinders, then it is critically important that you slow down the flow rate through the bypasses. Now, I know these things are designed that you've got pressure balance between the bypass ports and the output ports, and there are good reasons for that. But really, you're into the era of variable flow control with the way that we design boiler houses now. And ideally, you should kick your 3-port valves into touch and put 2-port valves in under proportional pressure control. But that's a big retrofit. One thing that you can do is you can turn down the bypass valve on a 3-port valve, and you can a typical isolating valve, you can turn it down to give yourself 25% flow. That makes a huge difference. Or you can put one of the range of Danfoss constant flow rate valves into the bypass to slow it down further, because you only need 5 or 10% of flow on the bypass to keep the circuit alive without actually putting a huge amount of the flow water straight back into the return. But of critical importance is that if you need to be focused on flow rate control, controlling pumps anywhere in the circuit on pressure means that you have no idea what's happening to the flow rates, and you might be able to set it up for one particular point of operation and it works absolutely fine, but for other points of operation it might be miles out. And one way of controlling pumps on flow is to use available heat meters. Using the flow output from heat meters, and you control the pumps against the flow rate set point. It works very well. So that's temperature dilution. Is that clear enough before I move on to the next bit for everybody? Okay, so now there's the issue of flow division. So what we have here is 3 gas, LPG or oil boilers in parallel on a low loss header circuit with just a flow header spur and a return header spur off the common header. In this case, does it matter which combination of boilers you use to meet the load? No? Well, the answer is no, it doesn't matter what combination of boilers you use to meet the load, because they're all gas or LPG or oil boilers. However, if the third boiler, boiler 3 on the right there, is a biomass boiler or a CHP unit, now does it matter which combination of boilers that you use? And it does, because you want your biomass or your CHP or possibly even a heat pump running in combination with low temperature boilers. You want that to run 100% of the time, and you want it to give 100% output. So in that situation, if the you've got 1100 kilowatts of boilers there, these are just random numbers. If the load is up to 300 kilowatts, you would only have the biomass boiler or the CHP unit running. But once that load exceeds it and goes to, say, 400 or 500 kilowatts, then one of those gas boilers is going to kick in. And the first thing that happens is that you've got 2 pumps running, one running at 300 kilowatts, one running at 400 kilowatts. So the one on the gas or oil boiler is running at a higher flow rate, and the flow is being shared between the biomass and the gas boiler. So immediately you're getting a lower flow rate through the biomass boiler, which means immediately it can't produce its full output. So the minute a gas boiler kicks in, the minute the load goes above 300 kilowatts and the gas boiler kicks in, the biomass boiler can only produce 3/7 of its output. And this is by far the most common way that biomass boilers and CHP are connected. I've been privileged to see various things before they were published. I've had a good work around the new CIBSE Guide B1, which is still yet to be published. It was a year ago I looked at it. And I hoiked out of there various diagrams which had biomass and CHP in parallel with boilers, because it's one of the main reasons why biomass and CHP do not give their full outputs when they run in parallel with other boilers. So if we look at 100% the load, if we now got the biomass on the right and two gas boilers on the left, say, 100% the load is supplied by the biomass boiler when only the biomass boiler is on. When you have a biomass boiler and one other boiler on, then the boiler 2, the gas boiler, produce 57% of the heat required. The biomass will produce 43% of the heat required. And in that situation, when all three are on, the biomass or the CHP only produces 26% of the heat required. So unless the load circuits are fully loaded, you won't get the full output from the biomass or CHP, except when the load is less than 300 kilowatts. So this is a frequently encountered system. And what I'm showing here is the combination of temperature dilution and flow sharing, which is typically found in boiler houses up and down the country. And you could go to probably half the boiler houses that you've designed and you'll find one or both of these problems. Yeah. Right. Right. I'm going to repeat the questions. This is being recorded and you're not being picked up. So, so the question is, what, in relation to the pumps into the boilers, what prevents the pump's flow rate being adjusted to make sure that it matches? And the answer to that question is it can be done, and it depends on the boiler manufacturer as to whether or not they require a constant flow rate through the boiler under all conditions, or whether they will allow you to operate a boiler at reduced flow. And I've got an example in a minute where I've actually solved this for a client doing exactly that. Okay, so if boilers are installed in parallel, it's not possible to prevent the return flow being shared between however many boilers are on, and by that I mean any combination of CHP, biomass or boilers. The only way to avoid it is to ensure the renewable generator, whether that be CHP, biomass, heat pump, even solar thermal, is the first heat generator on the return from the load circuits. And this requires a series connection, not a parallel connection. And it applies to any of that. So that was the first two elements I wanted to talk about, which was temperature dilution and flow sharing. Now I'm going to talk about various issues with retrofit designs that we have found and what we've done about some of them. So, and you'd be surprised how often this happens now. I don't know how many of you here work for consultancies and how many of you are contractors, but these problems tend to happen more with design and build contractors than they do with design consultancies. But we do know of some design consultancies that have made some enormous haulixies over these things. The first one here is a very big organization. They had their boilers replaced because their time expired, so they were replaced with boilers operating at 20 degree delta T. And then they realized, oh, wait a minute, the existing load circuits are 11 degree delta T, so we need to make that 11, but they forgot to change the header. So the header coming off the boilers and returning to the boilers, the common header, the whole thing was sized for a 20 degree circuit, yet the boilers and the loads were all running at 11, and there was nowhere near enough flow, almost half the flow that was required, as you can probably see, including the pump, of course, which was undersized. And then trying to run circuits at 11 degrees C of boilers which are designed to run at 20. In this case, you don't get the full output from the boilers because the returns are coming back at too high a temperature. And then if you've got constant speed pumps on the load circuits, you can be coming back with 2 or 3 degree temperature differences across the common header, and what you're really looking for is 20 to get the full output from the boilers. So in that case, the boilers don't produce the right temperature output. That's the header I just mentioned. Undersizing pumps as a result of these things. And then the last one is a really interesting one. I've made use of this in some of the designs I have done, but if it's missed, it makes a big difference to the performance of a circuit. You have a building, an oldish building, a building which was built in the 60s, say. It's got a cavity wall, uninsulated. It may have been double glazed. The roof standard is not very good. And so the owner makes the decision to cavity fill the wall, to put double glazing in, to improve the roof. Now, one system that we designed up in Orkney, they had done this to a 1960s building out on the island of Sanday. The system had a one-pipe radiator system in it. The heat load on that building dropped by almost 50% because they got rid of the flat roof. They put 150 millimeters of insulation on the old flat roof. They built a pitch roof above it. With double glazing and cavity wall insulation, the loads dropped by more than 50%. So the radiators, which were sized to run at 80 degrees, we reckoned would work perfectly at 50 degrees. And when we put in a heat pump system running at 50 degrees to replace boilers which used to run at 80, it worked perfectly. And we put a thermal store in series with the heat pumps, so they could dump a phenomenal amount of water into the heating circuits that start up each morning. And at 50 degrees, that building heated up twice as fast as it ever did on boilers at 80. And I put in 140 kilowatts of heat pumps to replace 320 kilowatts of oil boilers. So that was making use of the insulation properties of the building. We could use existing radiators, which were now desperately oversized, so they could be run at a much lower temperature. The opposite happens as well. But if you have a building which has been upgraded, but the people upgrading the plant room don't twig the connection between the upgraded building and the need to reduce the flow rate on the load circuits, you then end up with a situation where the load circuits are running at 2 or 3 times the speed they need to meet the load. So in temperature dilution terms, you've got the new boilers, which at 11 degree C boilers have been replaced by 20 degree C boilers in one particular case. So you've halved the flow rate on the primary lobe, but you haven't touched the flow rate on the secondary load on the load side, which were already too high. So you have about a 2.5 or 3 to 1 difference between the flow rate on the load side and the flow rate on the boiler side of the header, with massive temperature dilution. And this is where you get your 80 degrees drops down to 65, because you've got such a mismatch between flow rates. Now what that contractor didn't realise that he should have gone back and recalculated the loads on the circuits, because the building had been insulated, and having recalculated the loads, then adjusted the flow rates on those circuits to achieve what could now be a higher delta T, because the radiators are all oversized. Completely missed. Another problem that we found was a very large extension, including a swimming pool, was added to a building. And the IES simulation suggested that the capacity of the existing boiler house was sufficient to drive the new extension. But the boilers were shot, so they were being replaced anyway. The flow rates on the secondary side, on the existing load circuits, were all about 50% higher than they should be, but it wasn't spotted. So the IES simulation results were used to size the new boilers. That's a perfectly valid thing to do, but what was not done was that nobody went and actually measured the flow rates on the existing load circuits, because if they had have done, by the time they added those flow rates to the flow rates on the new extension, they would have found that the total load circuit flow rate was twice the primary boiler circuit flow rate. And again, massive temperature dilution, and this is the building with the high roofs where the wet radiant panels wouldn't heat up. Right, so this is what I've just been talking about. Don't use load modeling alone. Get out there with your thermometers and your pressure meters and go and measure flow rates. Before you touch an existing building, document what's actually happening. Don't just replace the boiler house and assume everything's okay down the line. Document what's happening, because you might well get a shock when you measure what's happening before you replace boilers. And then they've got the data there. It's invaluable data to help you to work out what to do. And what I'm going to show you at the end is the working out what to do. But this is quite common. That you put a new boiler house on and your existing load circuits run at 11, so you have very low return differentials coming back, but the boilers need high differentials to work properly. So this is a system that we looked at in the last year, and it had exactly this problem. By the time that the new boilers, which were designed to run at 20 degree delta T, were installed, the total flow rate on the load circuit was 11.8 kilograms a second, but on the primary was 5.2, so it was more than twice. And the best they were getting out of the boilers was 79, so it was coming back at 64, coming out at 79 because they were 20 degree C boilers. And that 79 was getting reduced to 71. And again, in this particular situation, the building was only used during normal working hours, but the facilities manager had to keep the heating running 24/7 even in the summer, because it took so long to heat the building from cold, he couldn't risk turning the heating off. So measure, and if you measure, you've got answers, you know. And look at existing circuits, look at the flow rates, work out what the flow rate, the total flow rate could be on the existing circuits, try to do a load calculation on those circuits, do modelling if need be, IES or whatever, or simplified methods, whatever, just to try to assess what was the actual load on that circuit. Now, what I do is I create simple models in Excel, and I'm going to show you one of these at the end too. There's a way of replicating what happens, and then you can do your what if analysis. You can change flow rates and temperatures and say, well, if I was to do that to that pump or do that to that circuit, then you know that you can sort out a faulty system, or you can design out a problem from the outset. Right, so this is another poorly designed system. What we have here is it's a modular boiler system. These were Wessex Modumax, which can be stacked in 2 or 3, and they have a header, prefabricated header bolts on the back of them. I'm sure some of you have used them. This had 3 stacks of 2 Wessex Modumax, 250 kilowatt modules. So there was 1.5 megawatts of gas boilers. There was a 500 kilowatt biomass boiler. Running into a buffer vessel. It wasn't a thermal store, it was a buffer vessel. Then into a heat exchanger before it went onto a district heating system. The first and most obvious silly here is that the gas boilers have been attached in parallel with the biomass boiler, so the biomass boiler doesn't actually have the buffer vessel to use. When you switch the biomass boiler off, the buffer vessel is there to capture all of its heat. And if you put the gas boilers in parallel with it, so you're charging the buffer vessel all the time, the buffer vessel can't do its job. So those gas boilers should have been on the other side of the buffer vessel there. That's the first thing. Now, the next thing is that as long as the load was less than the biomass output, the biomass produced 100%. But then, when any one of those 6 gas boiler modules fired, the common boiler pump, which was rated at 1.5 megawatts, switched on. And what happened was this. Now, the slight angle on the lines is because of the way Excel creates graphs. They should be vertical lines there. So the biomass boiler is the blue line. So up to 500 kilowatts, which is here, the biomass boiler produces its full output. But the minute a gas boiler kicks in, any one gas boiler kicks in, the biomass output drops to about 180 kilowatts. And as the load increases, the biomass boiler output gradually increases back to 500 kilowatts, but only when the total load is running at 2 megawatts. Now, in this case, what we recommended to the client was that we put a variable speed drive on the common pump on this pump here, the common pump to the gas boilers. Put a VSD on that. Use the heat meter which was on that circuit to measure the flow rate. So using a heat meter, flow meter in the heat meter, to schedule the pump flow rate for the gas boilers, and then the biomass output never dips below 390 and stays above 400 kilowatts nearly the whole time. Now that's 80% of its output, which is much more respectable than 25% of its output. Would make a huge difference. And this is without any physical engineering changes in the boiler house in this case. You could change the way that the gas boiler pump is scheduled so that the flow rate going through the gas boilers matches. And this answers your question about can you vary the flow rate. In this case, the Hamworthy, the boiler manufacturer, state we need a certain minimum flow rate through the boiler, which is the full flow rate through the boiler. But because it's in 250 kilowatt modules, then you can step the pump speed up at 250 kilowatts a time to match each boiler as it comes online. And doing that, you can get a much, much greater output from the biomass boiler. That makes a difference of something like 60% in the amount of the annual energy produced by the biomass boiler. It takes it up to about 85% of the annual demand, as opposed to something around 40 or 35. Right, this is the circuit that started it all about 4 years ago for us. We went into a boiler house and it had 5 Romea 600 kilowatt gas boilers, condensing boilers, across a common header. And another common configuration, the biomass boiler without a thermal store or buffer vessel was paralleled across it on the header. And that was a 300 kilowatt biomass boiler. Now, we were called in because the biomass boiler, the grate was buckling. It was overheating, the grate was buckling. They were taking slabs of slag out of the boiler, the size of one of these tables, and that thick, sheets of it. So it was clearly overheating severely. What was happening now, fortunately for us, the designers who had done this job decided to take the M-bus outputs from the heat meters, and there was more than that biomass heat meter in the circuit. They'd taken the M-bus outputs from the heat meters and fed them into the BMS. So not only could we read the kilowatt hours logged, but the instantaneous power output and the flow and the return temperatures. When we looked at the BMS logs, this is what we found, and you have to see it to believe it. Have you ever seen a boiler which is online whose flow temperature is less than its return temperature? No, nor have I. And we couldn't believe it either. And we looked at it and we looked at it and we got the client to check. This had happened over 200 occasions on the first year of operation. It beggars belief. And it actually happened. And the funny thing is, last week we were somewhere else looking at a big boiler house, and the energy manager said to us, "Funny you should mention that, because occasionally I've seen a negative temperature difference across our gas boilers." So that's twice I've heard of it now. But this is directly off the BMS logs at 10-minute intervals. And what we think was happening, we'll never know for certain, what we think was happening was that because the pumps were on the boiler flows, not on the returns, this is another case where the pumps were on the flows from the gas boilers, the pumps were pressurizing the header. So pressurized water was not only being fed into the load circuits, but pressurized water was being fed backwards towards the biomass boiler. We got as far as that. Okay, it's been sorted. There was also a significant problem with the biomass flue in this situation. And because there was insufficient airflow through the boiler, it combined with this hydronic problem to cause the boiler to go negative temperature difference occasionally, to produce slag, to burn out the grate, and all the rest of it. But that's a huge trap for the unwary. And of course, we had significant reverse flow up the header as well. This is all measured on heat meters. So. Sorry, speak up. Right, well, it was a number of things. The question was, how did we rectify the problem? I wouldn't say that we rectified it. It was basic, as is often the case. The client of a big organization goes back to their original design team and says, "Here is our report, go and sort it." We know that it has been sorted. We don't know how well it's been sorted. Sorting the flue at least enabled the excess heat to get out of the biomass boiler. That stopped the grate buckling and the slagging. And there have been no more reported instances of the negative temperature difference across the biomass boiler. They have also put in, we believe they've put in, because we recommended that they had a couple of huge redundant calorifiers in the boiler house because they'd gone to instantaneous hot water production. So we recommended they press the calorifiers into use as buffer vessels, and at least that way the excess heat from the biomass boiler would get dumped into that and so forth. So as far as we know, it's been sorted, but it's another one of these cases where you go in, you produce a report for a client, the design team goes, "Whoa," you know, they get all upset about what we've found, but you can't deny measured information, which is the beauty of having temperatures and pressures and flow rates and whatever, and logging it, particularly on a BMS. You can't deny that, and they've gone away and sorted it. A few of these I get so far with sorting, and we've had one really big job in the last year where we've sorted the whole thing. We've taken the lead on it for a big client and sorted a 4 megawatt boiler house, but that's the exception rather than the rule. All right, so when we wrote AM15, we had a colleague of ours who in fact was one of the authors of that original GR41 document all those years ago, and with me to work on AM14 because of his significant controls and hydraulic knowledge within CIBSE. He's regarded as one of their hydraulic gurus. And we had 18 months of hard bartering about what schematics would go into AM15. So if you look at chapter 7 of AM15, you'll find the first schematic is biomass boiler in parallel with gas boilers or oil boilers, and the second schematic is biomass boiler in series. And he insisted on doing it that way because of the potential control problems of having a fossil fuel boiler in a loop on a valve. Now, personally, I have done this many, many times. I've never had a problem with it, but you do have to be careful, obviously, especially the control of that to make sure this boiler doesn't overheat and that that this valve is open to allow some heat injection at the circuit and all the rest of it. So that's the controls engineers got to make sure they get control function right. Only put a biomass boiler in parallel with gas or oil boilers if the gas or oil boilers are there just for backup. But if the biomass boiler is rated at less than the full load, which is the normal situation, then you need to be able to take the temperature produced out of the thermal store, boost it, and inject it back into the circuit to get the desired flow temperature. Now, one of the beauties of this particular arrangement is that most biomass boilers like to work at temperatures higher than gas or oil boilers. Even the smallest biomass boilers can be run at temperatures approaching 90 degrees. And if you have a thermal store and you charge it to 90 degrees as opposed to 80, and you've got a 20 degree delta T on the circuit, you've immediately increased the storage capacity of that by 50% simply by running it at a higher temperature. You've then got the ability to mix that temperature down to what you want it to. And in terms of morning startups, that arrangement enables you to meet a huge proportion of the morning startup peak if it's correctly sized, without recourse to this. But when the flow temperature coming out of the thermal store drops below a certain point, as evidenced by the temperature sensor here, so this temperature sensor enables the gas boiler, and then when the temperature drops below your set point, it then starts to open that valve and the gas boiler starts to inject in a controlled way into that circuit, and a valve with at least a 50 to 1 turn down here, so you can inject very small amounts of heat from a reasonably sized boiler. That boiler can be both a backup boiler and an auxiliary boiler. It can be sized for the full load, and you can inject as little as 1 or 2% of its output into the circuit to maintain the temperature. And I've got lots of examples of this working very well now. On systems, probably about 800-900 kilowatts is the largest I've done it with. And I've had two oil boilers, two 450 oil boilers in parallel here, for example, on an injection circuit, properly controlled, works well. So if you're looking for the reference diagram, it's the second one in chapter 7 is the one to use. I would love not to have put the parallel one into into AM15, but you know, politics is what it is when you're doing these things, and you've got to reach a consensus about what works and what doesn't. But now several years on from having drafted that, I can now say with my hand on my heart, this works very well. I've not encountered any problems with this arrangement, and it is the only arrangement which will guarantee that you don't have flow sharing between boilers. Because in this arrangement, that biomass boiler runs flat out 24/7. If you've got a building that needs heat 24/7, this only kicks in as and when required, and when it doesn't, when it is required, the full flow is through that circuit, topped up by that. So you're not got flow division between two boilers because they're sharing the return flow. I don't know whether you can see this one. I'll just explain it to you. This is another one that we designed. We were working with a contractor who was putting biomass into Stobo Castle. And for those of you who have been to Stobo will know that there is a castle on the site, and that castle has got a small boiler house which heats the front part of it. They've then got a huge spa which has got a massive swimming pool and a small pool and 20 treatment rooms and saunas and all the rest of it in the spa. And the boiler house in the spa building heats the other half of the castle and the whole of the spa. It's got two 450 kilowatt Viceroy oil boilers in it. We'd done some load modelling of the spa and hotel buildings, and we reckoned that for the most part, the load was less than 200 kilowatts in all but the coldest weather. It's much more than that at start up in the morning, but for even in moderate winter weather, you weren't pulling much more than about 300 kilowatts. So a 200 kilowatt boiler or a 199, which kept us in the small biomass band and got the highest RHI, was installed in a boiler house up the hill. And to get the biomass boiler in series with the existing boilers, we put in a plate heat exchanger in the return line. And we've done this in a number of places. We've also done this at the new hospital on Mull, where we've got a 150 kilowatt boiler, plate heat exchanger in series with about 350 kilowatts of oil boilers. And it works extremely well. The primary and the secondary of the plate must be rated to take the full flow rate, obviously, because you're putting the full flow through it, which means that the primary has also got that full flow rate capacity. What you have here, though, is that the heat exchanger itself is another mixing node. If the flow rate in this circuit is greater than the flow rate in this circuit, even though there's no physical connection between them, you will get a reduction in the secondary flow temperature coming out of the heat exchanger if the flow rate here is higher than the flow rate here. But the flow rate here is higher than the flow rate here. There's nothing we can do about that. The pumps here these are main and standby boilers, so the pumps here are rated at 450 kilowatts on the primary circuit. But the pump here is rated at 200 kilowatts. So immediately we've got twice the flow rate on that circuit than on that one. But there is a solution that because biomass likes to run much hotter than oil or LPG, this circuit, which was originally designed to run at 82, we were told by the facilities manager there, or the engineer there, that it runs quite happily at 78 or 79. So we knew we could accept 3 degrees of temperature dilution. And we put the temperature of the biomass boiler up to about 87, which is the temperature at which that Hertz boiler would run happily day in, day out. So going in at 87 with a couple of degrees temperature drop across the plate, coming out at here at 85, so you're mixing the return water, which is coming back at about 67 or 68, with water at 85, and you're actually achieving your 79 to 80 degrees on the inlet to these boilers, which means that those boilers don't fire except when it gets very cold and the return temperature falls further. So just to put that into words, they behave like low loss headers. There will be there'll be a temperature mixing effect, although the water is not physically mixing. And it's something, I don't know how many of you install district heating systems, but it's something to take note of if you're ever installing HRUs. Because HR heat interface units tend to be installed by the district heating contractor. Often there is then a domestic contractor puts the heating circuits in the houses of the buildings. And that domestic contractor will go in the HRU and he'll whack the pump up to full, right? And so all of a sudden you've got a higher flow rate on the secondary side of the HRU than you do on the primary, and you get temperature dilution again. And they don't understand what's happening. So it's everywhere. Once you start looking for it, you'll find it everywhere. All right, so the primary flow temperature, which is what I was just saying to you, you need to take account of the what's often called the approach temperature, the difference between the primary flow in and the secondary flow out. I try to specify plates where that's no more than 2 or 3 degrees. If you just go to a manufacturer and say, I want a plate heat exchanger, you'll typically end up with a 10-degree approach temperature because you haven't specified it. Because a 10-degree approach temperature gives you a very small compact plate and it's cheap. Whereas if you want a 2 or 3 degree approach temperature, the plate can be 4 times the size of a plate with a 10-degree approach temperature. So beware of that as well. So you need to know what the temperature drop is and you need to control it if you're designing. And then you need to have a margin above that, so you run your biomass as hot as you can to make sure that you've got sufficient temperature coming out at the mixing node on the other side, that you get the temperature you want on the header. Now the only rider I would put on this is if we go back to that, I'll get there in a minute, go back to the previous circuit diagram. At this point here, you may well want to put in a thermal mixing valve at this point, because under very low load conditions, the approach temperature, if you've got a plate designed with a 3-degree approach temperature at full load, then you're only going to have a temperature drop of, say, 1 degree or less at part load. So you might go in at 87, comes out at 86. If you've then got very low load on this side, then you could end up with 86 on the header. So you may need to put a thermal mixing valve in here and control that on a control system so that when the temperature is coming out of the secondary of the plate too high, it's mixed down to what you want.
Is there a thermal store on the biomass side?
Sorry, the question is there a thermal store on the biomass side? Yes, the biomass boiler in a separate boiler house has a biomass boiler, back-end valve, biomass pump, 4-port thermal stores, 2 thermal stores. I think it's got 10,000 litres of thermal storage. Then it's got a pump going down the hill to this plate heat exchanger. Yeah.
Is the shunt pump there, is that running constant speed?
Yeah, the question is the oil boiler shunt pump running at constant speed? Yes, that is the way it was designed, to run at constant speed. Yeah. So it's one oil boiler or the other. It's designed to support, but not both.
Okay, so there's a shut off pump.
Yeah. Right, so the first thing I do when I'm called into a problem boiler house is I take measurements. So I measure the temperature at every node I can find, around the boilers, common header on the load circuits, flows and returns. If you're using a BMS to take temperatures, many BMSs are not maintained properly. It's not at all uncommon for the temperature sensor indications on BMSs to be several degrees out. So be careful of using BMS data. It may be okay, but you want to take 1 or 2 independent temperature measurements to check that it is okay. Correctly installed heat meters where the temperature sensors have been correctly inserted into the pockets and are correctly in touch with the flow of water, both in the flow and return, then they will give very accurate temperature readings. And then I use an infrared thermometer extensively. It doesn't measure the exact flow temperature in the circuit to within any better than 1 degree, but it does consistently give you the relative temperatures correctly. So it underreads on the flow by 1 degree, it'll underread on the return by 1 degree, providing you're measuring on the same type of rusty pipe or the same type of fitting or the same colour of fitting, because the surface emissivity is very important with an infrared thermometer. One factory I was in a long time ago, part of their, they had radiant wet panels running the length of the production hall in the factory, and half of it was the original black, but painters had been in and painted the other half silver of each panel, and the reported fault was, well, the heating's not working properly in that part of the factory, so you put your infrared thermometer up and you read the surface temperature of the black bit as 85 and you read the surface temperature of the silver bit as 55, and I say that's why I get the paint off. So beware of measuring on shiny surfaces because it underreads significantly. And then you take measurements of pressure and flow rates. So usually, I've got a digital pressure meter, a Danfoss one. You can dial in the kV of the orifice plate or the double reg valve into the meter, and then it gives you the flow rates directly, or you can measure the pressure drops and then use the curves. And if you've got heat meters, correctly installed heat meters, and that is correctly exactly within the manufacturer's instructions, they will give you accurate readings. Recently saw a heat meter on a 100mm pipe which was installed the correct number of diameters from a double bend, but because it was a double bend, the water was screwing through the meter and it was under reading by 30%. And after a long battle with the contractor, they moved it 10 diameters away from the double bend and it read correctly. So I construct a simple dynamic model, a simple non-dynamic model of the plant room, and I input all of these variables: flow rates, pump speeds, delta T's, temperatures, and so forth. And I aim to replicate the performance of the plant room. Now, this is just one very simple example of what we do. I do it on Excel. I just make up some symbols of pumps and boilers and pipes. So I put red for flow and blues for returns and rough. This is the model that I made for Stobo Castle. And I don't know whether you can see these numbers, but at the bottom there I'm feeding in at 86 degrees. It's coming out of the plate at 83. It's then mixing with the return down to 80.4. And that was with a load at 200 kilowatts on that circuit. So you've got this circuit which was pumping at 9.7 kilograms a second. This one's pumping at 6.5. So the flow rate in this primary circuit is 1.5 times the flow rate on this circuit here. In the end, I did away with that pump because that's just another loop. If you put in a plate which is in this case rated at 200 kilowatts, then you need a pump to pump out of it because you can't take the full flow through it. In the end, we put in a plate that was rated at 450 kilowatts. We did away with the pump. It's the same thing. So by varying these numbers, all the yellow boxes are the input, so I can change the delta T's, the loads, the set point temperatures and whatever, and it just goes once around the circuit and tells you what return temperatures you're getting. And it's very easy to construct that, and the only formula which are used are the temperature dilution formula at that node, the temperature dilution formula at that node. That's the only two bits of maths in this thing. That's all you need. And it just calculates the temperatures around the circuit. So if you're faced with designing something like this, all you need to do is to construct a simple model. You can then play around with the temperature and flow rates, and you can say, I'm going to have a real problem here, or if I adjust that by doing that, then we can get around the problem. And you can do this for any combinations. One job in the last year, we built a huge one. It was on screen size, it was about like that, with a big biomass boiler, 3 huge gas boilers, a massive circulating circuit, and about 5 or 6 load circuits coming off with complicated configurations on them and controls. So that's what we do. It's not beyond the wit of man to put this together, quite simply. It really isn't. It's very easy to do this. Once you've done it once, you'll see the benefit of it. Okay, folks. Any more questions?
Any more questions for David?
Well, if anybody, my email address is on the back of the presentation, along with my phone number. So if any of you want to ring me and talk about it, fine. If any of you want us to come along and have a look at a boiler house or system that you've been scratching your heads about, more than happy to do that. And I've got some business cards if any of you want to take one away for future reference. So.